Welcome to another video in which instead of telling you what I have understood, I tell you what I don't understand and see if any of you can help me. As part of my research project, Assumption of Physics, one of the things that we understood is that we're never going to be able to know exactly what the physical theories are about if we are not able to understand what exactly the mathematical tools we use are about. And therefore, there is this idea that we call physical mathematics, where all the mathematical definitions have to be motivated by the physics so that we know exactly what is the model, what are we modeling from the physical world. And so we have already been able to derive the notion of topology, the notion of real numbers from sort of physical ideas, and so that's fine. One of the things that I still need to work on is the concept of derivative, integral, and calculus in general. As you may or may not know, there isn't just one definition of derivative in mathematics. There are many approaches to calculus, some similar, some different, and that sort of brings up the question as what are the ones that make sense in physics and which one should we use, under what circumstances, how they should be generalized, and so on. So what I'm going to show you now are essentially a bunch of problems, a bunch of different definitions of derivatives that we actually use in physics. And again, the idea is, underneath all of this is, could we have one single definition, a general definition of derivative that is physically motivated, so we know what we're talking about, and gets us everything that we need, right? Can we have one derivative to rule them all, or we have to have like 2, 3 of them, and we have to understand what they are and so on. So, again, to people that come from physics and engineering, this might be surprising because we just always talk about the derivatives and we never really think about what's underneath. And so let's go through some of these definitions. So this probably is going to be a very rough video because probably one would need really a presentation to show all these things properly, but it would take an outrageous amount of time, and so this is what I'm gonna try and do it. So let's see what happens. So the first notion of derivatives that we learn is the idea that we have a function, let's say a y of x, and this is a function from the real numbers to the real numbers. These are real numbers and these are real numbers. And we can also plot it in our graph. We can have our x and our y, and there's going to be some function that does something like this, right? This is, for example, its position in terms of time for trajectory and stuff like that. Okay. The simple idea of derivative is that if we take a point here and we take a distance here, dx, so we pick an x, we get a dx, we are going to get some type of difference in y. And we can take that limit of delta y over delta x, and if this limit exists, we call it derivative, and it basically tells us the slope at this point of the curve. It basically tells us the tangent. Okay, so this is very nice. So this, what we have here is a notion of differential, right? And the derivative is a ratio of differentials. And we can think of this differential as these little infinitesimal differences that are not quite zero. They're just a little bit, but they're very, very small. Okay, so this is nice. Now the problem is that we have to generalize, and it's easy enough to generalize if we imagine that we have a function of r that goes to Rn. So now our y is we're going to put an index I here. Our y is a function that spans multiple dimensions. So we could imagine for example, that they're three-dimensional, so we have y1, y2, and y3 here. And we are going to have this function of x that does whatever it does. And so here would be, for example, x equals 0, and here would be x equal 1, and so on. So we go, we go and we go forward in x, and as we change x, we go through the whole curve. And again, here we can do something similar, because again we can imagine to pick an x here, and then another x, so we have a delta x, and this is going to be the other x, and this is going to be the difference in y. So we still have a delta x, we can still imagine our delta y, but now our delta y is going to be a vector, and we still can imagine to make the limit of this thing, and so we can still write something like dy vector and dx. Okay, this sort of works, okay. But now the issue is that we might have actual functions of multiple variables. So we could have a yi of xj. So this would be an rn, and this would have been n here. And this would be an rm, right? So we go from n variables to m variables. And now we have a problem, because if we try to do the same thing with differentials, you know, if we can imagine to have a delta y, and we can imagine also having a delta x, the issue is that this makes no sense. The delta y over delta x makes no sense, because there is no division for vectors. And so this does not work. But we still need a notion for derivative. So what you do here is you define the derivative in a slightly different way. What you do is that you assume that these two spaces, Rn and Rm, have a norm, right? That you can get a vector x and take the norm of this, and you can take a vector y and take a norm of this. And then what you're going to do essentially is, instead of making this division of the vector, you make the division of the norm. And but you still need this function defined, and this function derivative is going to be something that takes a vector in x, let's say, and gives us a vector in y. So what you do is you take essentially delta y. You say that there is a function a that takes vectors from x to y. So this is something like this. And this is going to be a linear function, and it would take our vector delta x. There you go. And then you take the norm of this. And you divide this by the norm of delta x. Okay? So now you make the limit of this thing, and you want this limit to be 0. Because what really happens is that this a here is really the derivative, and the derivative is taking the delta x and gives a delta y here, and then you're taking the difference between the delta y, and you want that thing to be 0, essentially faster than what the delta x does. Okay? And so this essentially works. So, you know, when we talk about derivative in multivariable calculus, this is exactly what we're using. This is called the Frechet derivative. Frechet, I think there is an accent there. Okay, and this is a little bit clumsy, right? Because we kind of have lost our nice notion of differential here, and the derivative is not quite a ratio of differential anymore. And this is this weird thing that we can do. We can have a differential of a space that spans multiple dimension up, but we can't have down. And when we do it, we get these things that it's a little bit of a mess. Is there any conceptual problem with this from the physics side? Well, Kind of, because we have to assume that these spaces have a norm, and many times we don't have a physical norm that makes sense. So imagine that this is a function that actually takes a point in phase space of position and momentum and returns either something else, right? But x is phase space, is position and momentum. A norm would basically mean that if we have a vector here, or a vector here, or a vector here, right, we know how long that vector is. And here is the problem, that we have a norm on Q, which would be the distance, and we have a norm on P, which is the momentum, but there is no way to compare those norms. So there is really no way for a norm in phase space to make sense, because is this vector bigger than that vector? Like, is the vector in P, this one here, bigger than the one here? It doesn't make sense, because we really don't have a notion of distance. We don't really have a notion of a norm there. And of course, you can impose it. You can pick some units in P and pick some units in Q and say that that's the norm. But it's not a physical norm. It's like a mathematical trick that you're using to make your math work. And this is exactly what I would not want to have in physical mathematics. I would like to have everything strictly defined from physical ideas. So, okay, there is this little bit of a problem. But there is another derivative actually that one can define that does not quite need a norm. So let's look at that real quick. Okay, so we still have a function y of x, and now these spaces here are not normed spaces. They're what they're called locally convex topological vector spaces. So it's a vector space, so the idea that we can have addition and scalar multiplication. And locally convex means that around each point you can essentially imagine all the neighborhoods around that point as something that sort of kind of looks like a ball, like it's something that you can contract, and it's convex, meaning that all the points, all the linear combination are inside these things. It would be a little bit more technically complicated. And there is actually a physical reason why we could assume that the spaces that we're used to are locally convex, and it has to do with the other work that we're doing in ensemble spaces. But for now, whatever, it's just a mathematical definition. It's this, and all our n and even function spaces satisfy, a lot of function spaces satisfy these things. Okay, so we have these locally convex topological vector spaces, and we still have the problem that we can't really divide vectors by vectors. So what you do is essentially this trick. You take y at a value x, and you sum it with some coefficient that we call a, and now this is a real number. And you take your delta x here, and now your delta x is a vector. And during the limit, you keep essentially this vector constant. Yes. And you subtract this with y of x. So this is essentially our delta x. But then what you do, instead of dividing by delta x, which you can't, you just divide by the real number. So it's like you're making a directional derivative. You're fixing the derivative, and then you go closer. Your delta x is going to be shrinking along a particular direction, and you define this. And if these things exist, then this is going to be the derivative of x and y at the particular point x with the particular direction delta x. Okay, that's basically how it's going to work. And so you have kind of something that works, except that this derivative, if it exists, it's not necessarily linear. Not necessarily linear. So if it exists and it is linear, it's going to be the same as taking the Frechet derivative, but if not, it's doing something else. And still it doesn't really tell us why this notation still makes sense, because we're not really dividing by a differential. It's kind of like, what is this doing exactly? It's again, it's a little bit murky. It's not exactly like squeaky clean as I would have it. But okay, so these are the sort of the definition that we currently have, and there are other approaches to these type of things of sort of derivative as limits, but we leave it as this, right? Now, the issue is that these are not the only type of derivatives that we actually use in physics. Or in mathematics. There is another concept of derivative called the Radon-Nikodym, and let me check the spelling before I botch it. Radon-Nikodym. There you go, Radon-Nikodym. I never remember which one is the Y and which one is the I. And this applies to measure theory. And so if you don't know what a measure is, well, you take, let's suppose that we have a real line, right? And we have, let's say, all possible intervals on the real line. And what we're going to do is that we're going to create a measure mu that goes not from the real line, but what is called the sigma algebra, which is sort of the set of all possible subsets that are nice in some way. If you don't know what it is, it's not that important, and it's going to give us a number, right? And so if you imagine, for example, the size of the interval, that would be a measure defined with this idea. So you give me a subset, and I can tell you how big it is. Probability is also measured. You give me a subset of the real line, and I tell you what is the probability to have that something that the particle is there or something like that. So measures are really useful because you do it, you use them for probability theory. It's another way to define integration. It's probably one that makes more sense. And the idea is that if you have two measures, you can define a derivative between them. So just to make, just to imagine, suppose that we have a three-dimensional space and we have a notion of volume, right? So if I give you a little volume, let's call it, I don't know, sigma, let's call it sigma, whatever. If I got a volume sigma, you are going to give me a real number, and this is going to be the size of the volume. And I imagine that there is charge distributed there, and so we are going to have another measure that tells us how much charge it is. So again, we give it a volume, and this charge, this function is going to give me a number. Again, it's the number, the charge within that volume, right? So that's the idea. And these measures are additive, meaning that if you have two regions that are disjoint, so for example, if I have a sigma 1 here and a sigma 2 here, then the volume of sigma 1 union sigma 2 is equal to the volume of sigma 1 plus the volume of sigma 2. And this is going to be the same for the charge and so on. So this is kind of the property of measures, and we can use this to model charge and model volume. And then the idea is that, again, you can imagine that you take a small region and you see how much charge is there in that small region, and you divide it by the volume. So you can imagine that for a finite volume, for example, we could calculate the charge density that there is in that volume. And now you can imagine of shrinking that volume and making it smaller. So you make a limit of this such that this goes, let's say, to a point x, right? And of course, so the volume is going to go to zero, the charge is going to go to zero, but the ratio is going to go to what is called the Radon-Nikodym derivative. So, and this would be the derivative between these two measures. And how is this related to the previous derivative? Well, if this space is a single dimension, then the Radon-Nikodym derivative is exactly the other derivative that we have. Okay, and this is actually it's a very important and very physical way of thinking about this, about things, because if you think about volumes and charges are defined physically on finite volume. A lot of the time in physics, when you do E&M, electromagnetism, you talk about a charge density rho, and you start from that, and then you integrate the rho over a volume, and we should call that sigma for consistency. You integrate that over a volume, and you get the charge in that volume. And this is completely backward, because in physics we don't define charge density first and then integrate. We define the charge density on finite volume, we define volume size on finite volume, and then we imagine of making the ratio and making it smaller and smaller. So in a sense, the Radon-Nikodym derivative is very nice because it's very close to what we do in physics, and it would make sense to have some type of derivative like that. In fact, there are a lot of other cases where something like that happens, but it's not quite the Radon-Nikodym derivative, because it's kind of a directional Radon-Nikodym derivative, and that's kind of the type of thing that I'd like to have generalized, but I haven't quite seen it. So if we imagine, for example, that typically you imagine that you have a force, right? And the force then you apply it over a path, right? So imagine that you have a path and there is a force field around, right? And you want to calculate the work. You're going to say that the work is going to be the integral of the force along the path times the distance, right? And that's called this gamma, and that's called this gamma. But again, if you think about it, it's kind of backwards, because the way that we measure force is essentially to I don't know, have something like a spring and apply the force and see how much the spring is displaced, and then we say, aha, this is the amount of the force. So at the end of the day, what we do is that we measure the work, we measure the distance, and we calculate the force. And again, we can imagine that we're making infinitesimal displacements in distances that makes infinitesimal work. So really, the way that you can think it about is that you have something x of lambda that tells you the distance between the initial and the final point, right? So it's kind of a delta x. And you have another w of the path that basically tells you the work. And then you are kind of taking the work along the path, divided by the distance along the path. You made some limit when the path really goes to a point x, and this is going to be your force. And because the path is going to have a direction, so there is a possible I here, this would have a possible I here, and it would be a covariant vector. And so we can put this I here and I here. So it makes sense from a physical perspective to have these things defined in this way to sort of mimic the Radon-Nikodym derivative, and that's not exactly what we have. Something else that is very similar would be for the magnetic field, right? We measure, we're going to have a surface at this time, and we can measure the magnetic flux phi, and we're going to have a notion of area of this surface A. And so again, you're going to have a magnetic field, and typically you're going to write that the flux is the integral on the surface of B cross the sigma, right? The infinitesimal area multiplied by the vector, by the magnetic field, and you get the flux. And again, we measure the flux and we measure area, and those are the prime things that are actually connected. And then in the limit that we make this surface is small, you will get the magnetic field. So again, you imagine that you make the limit where the sigma goes, let's say, to 0, to a point, and you are going to have the flux of sigma divided by the area of sigma, and you're going to want to say that this is really the magnetic field. And the direction of the magnetic field is actually going to be the sort of the direction of the area. So these are the kind of thing that I like to have, and we don't. We have something very similar in differential topology, which basically takes a whole other subject here, because you can kind of imagine this F being a one form and B being a two form, because that's kind of what they are. But there is a problem with that, is that the definition that we have in differential for differential manifolds are not quite exactly what we would want them in physics, and they're kind of double dipping, because they again create a new notion of differential and derivative that is different from the other, and there's kind of like there is a mismatch. And again, if this would be a lot more sense if you know how these things work, but let me try to give you a sort of the general idea. So you have a definition of a manifold, right? A manifold is a topological space. If you don't know what a topological space, it's not important at this point, but the point is that it's the thing that characterizes the manifold is that it's a space that at every point looks like Rn for a particular n. So for example, again, a sphere, right, is the surface of a sphere is a two-dimensional manifold, because at every point we can imagine that there is a neighborhood, and we can imagine that is isomorphic to R2. You can make an invertible map between this neighborhood and R2 that does not break continuity. That's basically what it means. Now, to give you a more general sense of what a manifold is, it's basically any set of points that you can identify with variables. So, for example, if you're doing a blood work, the blood work, right, so your result of the blood work is going to be a bunch of entries with a bunch of numbers. That's a point on a manifold, right? So, a lot of things that we do in science are basically that. The important thing is, though, that this list has to be finite, right? There has to be finitely many numbers. It can be very big, but it has to be finitely many numbers. So something like a function space is not a manifold, because you would need infinitely many numbers, and that sort of makes it a very different. So anyway, there is this notion of a manifold, and manifolds allow you to have a different coordinate locally and talk about things and so on. And that's sort of the mathematical way to treat these points, these spaces where each point can be thought as can be identified by a set of finitely many variables. Now, there is a notion of differentiable manifold, and a differentiable manifold is a manifold where whenever you make a coordinate transformation, so let's say that you're here with this set of coordinates, you're going to go here and you have a different set of coordinates, and of course on the overlap things have to make sense. The idea is that if you have a differential manifold, every time that you change coordinate, the transformation is differentiable. So the Jacobian is always well defined, essentially. So you can say that if I have a coordinate y, I, and I go to xj, then this thing is always well defined. The Jacobian is well defined. Okay, so now we still have the problem of, okay, what does it mean physically that the Jacobian is well defined? Yeah, it's convenient, fine, whatever. But what is it that physically we're requiring to say that the space is nice? So, for example, if you imagine something like this, something like a line with a kink here, right, that space is not differentiable because there is the kink here, and that you don't have a tangent defined over there, and then you have something nice and smooth, then things work fine. And you could imagine that these are sort of topologically they are similar, so you can imagine to have a one-to-one map that maps a coordinate here to a coordinate here, and but that map would not be differentiable, and therefore it would change the differentiable structure. So in a sense, when you are picking a differentiable manifold, you're taking a manifold and you're choosing a differentiable structure. And again, what are you doing physically? What is it that you're selecting there? It's a little bit murky, and it's not clear. But anyway, the point is that you are the derivative between the coordinates is always well defined, and typically the definition is the Frechet derivative, which is going to have those problems. But then what is interesting is that on top of these coordinates now, you want to construct objects that are coordinate invariant, and you're gonna sort of construct objects that are very different from what you would expect. So you define vectors in differential geometry, differential topology. You typically define them as a map that takes a function, a smooth function of your space, and gives you back another function in your space. And that basically, this vector has to have some other rules on top, and it makes it so that this vector is essentially a derivative with a particular direction. So in component notation, you would write the vector as something like this, vi partial I, right? And this, you imagine that you're summing all over the I. And so what you're basically doing is a directional derivative. You're taking the derivative in a particular direction, and now you can imagine that this thing takes a function f and returns the derivative in that particular of this particular function in that particular direction. And now you already have a problem here, because if the vector that you want to describe are velocities, well, velocities are not derivative. We would like to keep that notion of a vector of something with a displacement that we move around. Right? That thing is lost. And you can kind of recover it because you say, okay, this is isomorphic to the other thing, and so mathematically are the same. And this is exactly the problem that we have now in physics with the very big mathematization of the physical objects, is that we don't have objects that are exactly what we think they are. They're kind of like the same because mathematically equivalent. But the fact that they're mathematically equivalent, they're not the same objects. And again, we want to have definitions from the physics that tell us what these objects are, and this is not quite the way to do it. But worse than that, you define then differentials in differential geometry, differential topology, as something like, for example, the x, as something that takes a vector and returns a number. And the idea is essentially that this is what you do when you're integrating. So when you integrate something and you have dx here, what this thing is doing is taking some vector, displacement for me, and gives you back a number. That's the thing that you are integrating. So the differentials are defined like that to essentially allow you to do integration on top. And the differentials are one form, and then you can also have k form, and a k form omega. It's something that takes k vectors and gives you a number, and it's fully antisymmetric, such that omega of, let's say, v is equal minus omega of wv, and this is because if you imagine that you're integrating these things, right, you're basically integrating areas. And when you're integrating areas, you are actually integrating determinants, and therefore you have these transformation rules. But okay, these are the things that we'd like to reattach to those forces, to the magnetic field, to the sort of charge densities, right? We would like to think about those things as the thing that we are actually integrating, but now we have the problem that these are actually not quite defined like that, because again the vectors are these displacement. What does it mean that I'm taking a derivative? They're not displacement, they're derivatives, so we're taking derivatives and integrating them. That doesn't quite make sense. And then the notation sort of follows some of these other ideas, and again the idea that a force is itself a differential does not quite work in our head. Like, we would like to write integral of fi dxi, and so we would like the differential to be the vector, the thing, that the displacement, while the force being the one form that we can say. So we have all these issues that we need to sort of put together, right? The idea is that we would like to understand, okay, what is really that is happening? Why were we using derivative in physics? And what is a good way, possibly the most general way that we can think about them? And can we turn those ideas in mathematical definitions and get one definition of derivative that works? And of course, I have no idea how to do it. I have some pieces that I think could work. And one of those general piece starting point is this idea that I was saying before. In physics, we start with finite things, and the infinitesimal is what we get when we make some sort of idealization. So, for example, as we said before, we have volumes and we have charge, and these takes finite volumes, right? And we imagine that these volumes and charge can be defined on smaller and smaller and smaller volumes, right? And this is an idealization, because in practice we do not know that we can define volumes that are always smaller and smaller and smaller, and probably we cannot, because there is a Planck scale, so at some point we're going to stop. But we make this classical assumption that everything is infinitesimally reducible. We can make things, we can break things into parts, and so even this space, which region sigma, can be divided and divided and divided and divided and so on. And I think that's kind of the idea. That's what we're doing, right? We start with something finite, and we assume that it can be broken up, and we assume linearity. We assume the fact that the volume of sigma 1 with sigma 2 is equal to the sum, right? And we do this for a lot of quantities, right? We even think about mass as something that works like that, even though we know that can't be completely true, because mass is energy, and energy, we know that it's not always true that the energy of the whole is just the energy of one region plus the energy of the other region, because if there are interactions at the boundaries, then things don't work out like that. You can't just say, oh, there is the energy on one side and on the other side. So again, these are kind of approximations that we can imagine that work at large scale, and we imagine these things to work. And because we have this idealization that we can always make things smaller and smaller and smaller, then the idea is, then we can talk about these limits and so on, right? So the fact that we say that our volume is equal to the integral of infinitesimal volume in infinitesimal pieces is essentially assumption. The fact that our line gamma is equal to the integral of some gamma, right? Not really in integral in a sense that we are integrating a variable, but it's really the sum of all these pieces, right? That this whole thing is the sum of all these pieces, and this whole thing is the sum of all these pieces. And of course, if we have some kind of charge, it's going to be the same. The charge on sigma is going to be the integral of the infinitesimal charge that we have defined on the infinitesimal volume, right? So that's essentially what we are doing, and that's what we are showing. Now, if we imagine that this is the case, that that's what we're doing, we're essentially taking a whole and approximating the whole as the sum of these infinitesimal pieces, I think we get a sense of what differentiability is. Because if we imagine continuity, right? The continuity, we have a very nice notion of what it means physically. It's that we always have, if we have a point here, we have a point here, we can go there and we can go there in very small steps, and these steps again can get smaller and smaller and smaller. So we have a sense of what continuity means physically. For differentiability, again, now that we have this idea, we are approximating these lines with small pieces, right? So suppose that we have this line here that has a kink, right? And we can imagine that we are approximating this line with we make it in small pieces with a lot of small segments, right? And we are approximating it with also a small segment here, and this is fine. But at some point we arrive at the kink, and we say we have to go here and we have to go here. And so we close this segment in a different way. Now, imagine if this is nice and smooth, if it's differentiable, and we're making this approximation by making all the basically a polyline out of this. It doesn't really matter how we make the polyline. If we make the polyline small, if the thing is smooth, what's going to happen that each segment of the polyline will approximate the tangent, will tend to the tangent, and therefore all these polylines will converge in the same way. But if you have the kink, right, you can imagine that you can arrive with the kink sort of with the same angle like this. Or you can imagine that you're approximating the kink in another direction. And so when you arrive to the kink, it's not well defined where, what direction you're going to for your polyline. And so you have all these different approximations that are not equivalent for that small segment. And so what you have to do, if you're making approximation now, well, you have to be aware that there is a special point. And that special point is where the space is not differentiable. And so the differentiability of the space is basically telling you in what way you can make these limits work. And so if you have a coordinate chart that is differentiable within the differentiable structure, what's going to happen is that you can make your polyline approximation without worrying that there are some points where things are not going to go well. And so this gives me a sort of an intrinsic way to understand differentiability in the same way that I have for continuity. So I don't need a map. I can understand what's happening within that space. So I can imagine this curve being differentiable because it has a particular property and not because it's a map from a space to the other and that map is differentiable or something like that. So I like this and I think this works. So I think this is one part of the puzzle. Another part of the puzzle is understanding what the actual derivative is, and can it always make sense to think it in terms of a ratio between differentials. And here what I'd like to do is having something like this. I have the space of, let's say, time, right? And these are all my possible value of moments in time, and this is going to be R. And then I have a space that is space, a physical space, so it's going to be R3. And I can imagine I have a map from t to x, which is my gamma, right? And this is a function from t to x. So it tells me for each moment in time, where am I? And now I can imagine that in the same way that I have these spaces here, I can make these sequences of differences that become smaller and smaller and smaller. And I want to be able to define something analogous to the tangent space as the space of sequences in some way. And I think we have done it. But that you know, it's a space of sequences of things that become small. They become small in a certain way that makes sense. And I'm going to have the same thing for x. So now we have for each space, I have the space of the points, and I have the space of these sequences that become smaller. And now I can ask, well, whenever I have this sequence that becomes smaller here, I can plug it here, and I will have a sequence that becomes small, right, on the other side. So if I make the interval in time small, I will get the interval in space that is becoming small. And the thing is that, as I said, these are sequences that are well behaved in a sense that they converge to zero, like they become small, but on a particular direction, within a particular direction. So if you imagine that you know, in time, for example, you are getting smaller, but you are not doing something like that. You're not flip-flopping all the time so that you don't know which direction you are in. And in space, you are going to zero, but you're going to zero from a particular direction, and you're not doing something like this. You're not circling around, right? And if the map is such that when I plug in an infinitesimal of t, I get an infinitesimal of x, then that's when I say, okay, the map is differentiable. It's mapping small well-behaved things to small well-behaved things. And then I can define my d gamma over dx, over dt. And this would be the velocity. The velocity is essentially a function that is taking an infinitesimal displacement in time, and it's giving me an infinitesimal displacement in space. And so, because what I basically write, I can write dt dx, there you go, dx is equal of dx dy multiplied by dt. And so this is my infinitesimal displacement, my differential. Things are becoming smaller, and things are becoming smaller on the other side as well. And so now this thing, instead of thinking it as a ratio of between two differentials, right? Instead of thinking of something that I actually do a division, I think it as a linear map. It's something that it's taking, oh man, this should have been a t. It's something that it's taking a t and it's giving me an x. It's taking a dt and it's giving a dx, and I write it like that because what's happening is that these two things are cancelled out and so on. So the notation makes sense in that way, not really because we're doing a division, but it's because it's a linear map. And once we have that, the idea is that we can do it for whatever we want. And now we could have another space that we call y, which would be, I don't know, r to the m. And we are going to have a map that is going to be y of x. And here we are going to have, again, the space of differential dy. And here, if this map is well behaved because it maps differential to differential, then we can literally define dy dx. And we can write that dy is simply dy dx, the derivative, over dx. And again, this makes sense because this notation, again, does not really mean that we're dividing vectors with vectors. It's just a linear map. It's something that takes one thing and spits out another thing. And I do think that this can be made precise, and I think that this video is already too long, so I'm probably going to stop here. But I'll put a link of sort of the notes that we have. And so the idea is that I think it's possible to define a derivative on these in this way, with basically thinking about how these defining differential as things that become zero in a well-behaved way, where there is a tangent essentially to the way that they go to zero, and differentiable maps as things that map differentials to differential. And what is nice is that the way that we defined this differentiability works, we think, in a generic topological vector space. So the only thing that we need is that we need to have a vector space that define these directions, so that we can tell, oh, we are converging to zero nicely within a particular direction. And so it's very general. We don't need the norm, so it's okay physically that that we have positional momentum, and we can't really get a norm of that. And what is also nice is that we have something like the sort of a Gateau type derivative. We're making just a derivative succession and calculating it. And we get that thing to be linear. Like if it exists, it has to be linear. The linearity is not that something that we have to kludge in like you do in the Fauché derivative. You define it to be linear. And it's not like the Gateau derivative, where you can say, well, we have the derivative, it might not be linear. No, if it exists, it's linear. And I think we can also get a lot of interesting properties with that. So this is kind of what I'm working on these areas. It's quite a lot of fun once you get to play around with this idea. Whether I'm going to be able to get essentially one derivative where everything makes sense, I don't know. But one good thing is that these pieces could also be, this differential could be in spaces of volumes or spaces of surfaces, because those themselves locally they become linear spaces that you can combine. And again, I haven't found a theory for doing those things rightly done. So if any of you is mathematically inclined, more mathematically inclined than me, and you have suggestion and you want to help me figure out, please let me know. I'm not that hard to find. And I hope this was interesting. As I said, this was a little bit of a mess. It reflects the idea that I'm still trying to figure things out, and that the problem is actually not trivial. And yeah, and I think I'll give you, if you guys are interested, I'll give you some updates from time to time and tell you how things are going, maybe in a more structured presentation. Thank you again for your attention, and see you next time.